Assalamualaikum warahmatullahi wabarakatuh, and hi everyone. In this video, we will be presenting about ultrasound wave in ultrasonic sensors for the subject Physics 380. The members of the group are Alicia, Mimi, Lily and Alia Maisara.
Introduction to ultrasound wave. I will begin by introducing ultrasonic sensors. Ultrasound refers to sound wave with frequencies above 20 kHz, which is higher than what humans can hear, Urata 2021. These sensors work by emitting ultrasonic sound wave and detecting the echoes that return after bouncing off objects. By calculating the time it takes for the sound to return, a method called time of flight or TOF, the sensors can measure distance accurately. One of the key advantages of ultrasonic sensors is their ability to operate in environments that are challenging for other types of sensors. Unlike optical sensors that depend on light, ultrasonic sensors are not affected by dust, fog, darkness, or even transparent objects like glass or clear liquids, max-botics. Because of this, they are widely used in various industries, including industrial automation, where they monitor liquid levels without contact, in automotive systems for parking assistance, and in robotics for obstacle detection and navigation. Thanks to advancements in MEMS technology, ultrasonic sensors have become even more efficient. MEMS allows the sensors to be smaller, consume less energy, and achieve longer detection ranges, some reaching up to 9.5 meters while maintaining high accuracy. Modern sensors also feature temperature compensation and built-in signal processing, allowing for stable performance even in changing environmental conditions. In conclusion, ultrasonic sensors offer a highly reliable, adaptable, and non-contact method of sensing, making them a critical component in many modern technological applications. Next, explanation related to scientific instrumentation and application concepts. Now I will explain how ultrasonic sensors work based on scientific instrumentation. First, ultrasound wave are sound wave with frequencies above 20 kHz, which is higher than what humans can hear. That's what we mentioned in introduction. So these waves are very useful because they give accurate measurements and are not affected by light or object color. Ultrasonic sensors work using the time of flight principle. Inside the sensor, there are three parts, which is a transmitter that sends out the ultrasonic pulse, a receiver that detects the echo, and a microcontroller that calculates the distance. The sensors send out a pulse usually at 40 kHz. The sound travels through the air at about 344 meters per second. When the sound hits an object, it reflects back. The sensor measures how long the sound takes to return and uses this formula to calculate distance, which is distance equals to speed of sound times time over 2. This method gives very accurate distance readings with about 1% error. Some physics concepts affect how well the sensor works. First, acoustic impedance controls how much sound reflects from different materials. Attenuation means the sound weakens as it travels. Frequency selection is important too. Lower frequencies can measure farther, while higher frequencies are more precise. For example, 40 kHz sensors can measure up to 10 meters, but 400 kHz sensors work for short, precise measurement. Ultrasonic sensors are used in many areas like non-destructive testing, to check materials for flaws, and in robotics and automation to detect obstacles even in fog or darkness. Thanks to new technology like MEMS, these sensors are now small, accurate, and very useful in many industries.
Next, how do ultrasonic sensors work? Ultrasonic sensors work by emitting high-frequency sound wave, also known as ultrasound. These waves travel through the air until they hit an object in front of them. Once the sound wave hit the object, they bounce back and return to the sensor as echoes. The sensor then measures what's called the time of flight, which is the time taken for the wave to travel to the object and back. Using that time, the distance to the object is calculated using the formula distance equals the speed of sound multiplied by time and divided by 2. This method allows the sensor to detect objects and measure distance without any physical contact, and it is known for being highly accurate. For example, ultrasonic sensors in parking system. The ultrasonic sensors in cars work by emitting high-frequency sound wave from the bumper. This wave bounce off nearby objects and return to the sensor. The system measures the return time and calculate the distance. Then, the sensor sends this data to the car's computer. The driver is alerted through beeping sounds or a visual display, helping the driver to avoid collisions while parking.
So, we're coming into a parking bay here. We'll test the front parking sensor first. So you can see that 360-degree camera is handy for getting us into the bay. We're approaching an object at the front of the car. Those sensors are now emitting those sound waves, determining how close we are. And as we get closer, you see the intensity of the beeps increase, and then finally you get a red indicator showing you that yes, you are hard up against that object and you don't want to be going any further. Okay, what about reverse parking sensors? It looks like someone's put a suitcase in the way. These work in the same way, but in reverse. Let's see what happens as we approach it. Okay, the car has just slammed the brakes on. It's come up saying emergency braking. Now, the reason it's done that is because this car has reverse AEB. So it works the same as AEB does going forwards. It stops the car if you don't, as you're about to hit something. Now, imagine if that was a kid or a person that's walked behind your car. It's able to use those ultrasonic sensors to detect that and slam the brakes on so you don't hit them. This is crucial technology and why we think it should be fitted to every single new car today. Now, but you're wondering, where does the radar come into play in all of this? Well, an ultrasonic sensor only really works well 3 to 5 meters away from the car. The radar, on the other hand, can look further down the road, and these side radars built into the bumper bar are used for things called rear cross traffic alert. That's able to detect cars, pedestrians, cyclists that are walking, driving, cycling towards the car. And when you're wedged in next to an SUV like this, and you really can't see anything until you're well and truly in that line of traffic, this is where it's going to come in handy. So let's give this a shot. So I'm reversing out of the park here, and there's a car coming right there. Ooh, okay. So it has automatically slammed the brakes on, given me a warning that there was a vehicle coming, and you can see here that I still can't see beyond this SUV. So had I have not seen that, there was every chance that I would have run into that. Obviously, people are meant to drive out slowly and be careful, but in situations where you have a car that's moving quickly or you're just not paying attention, this kind of technology could potentially save you from having a nasty.
Example of real-world implementation. The first one is automotive. Tesla self-driving cars use 12 ultrasonic sensors to detect nearby objects like other cars or obstacles. These sensors help the car avoid collision, especially at short distance. The second one is industrial. Industries use ultrasonic sensors to measure water levels in tanks. This not only helps to effectively store water in the tank, but also prevent water wastage and reduce costs. The last one is injection molding. Ultrasonic sensors enable non-invasive monitoring in injection molding. This will provide data on polymer morphology, exact temperature and pressure of the polymer melt without directly contacting the material.
Intelligent flow monitoring. System cooling. The intelligent flow monitoring system for molds. Until now, consistent production of fault-free moldings has been near impossible to control with any precision. Using revolutionary new technology, system cooling offers an affordable solution for monitoring flow and temperature through every circuit within an injection mold. Sensors within the unit digitally monitor the return leg of all flow circuits within the mold, recording data, both flow and temperature, for every circuit. The interface module allows multiple manifolds to be easily connected and all monitored at the same time via the touchscreen digital display. From the second the water enters the system cooling will monitor and display the performance of every circuit. The software offers a very simple visual guide to the performance of the cooling system. Alarm limits can be set for both flow and temperature, meaning any deviation of tolerance can be easily identified. Alarms are displayed on the touchscreen and on the interface module, where an alarm output can be interfaced to the injection molding machine. The compact design enables system cooling to be mounted next to the machine platens, keeping the hose runs to a minimum, improving flow rates and reducing cycle times. And the remote-mounted interface allows easy monitoring from a convenient location. As water flows through the system, the sensors continually monitor flow rate and temperature. The compact sensor uses the vortex flow principle. The bluff body creates small eddy currents, and by measuring the pressure within these vortices, we can accurately measure the flow rate. Easily accessible and precise data that can be stored in the system's internal memory, guaranteeing ultimate traceability. Increased accuracy, greater productivity, and reliably perfect molded components time after time. The intelligent flow monitoring system.
Potential benefit of ultrasonic sensor. The first one is ultrasonic sensor can operate in both well-lit and dark environment without being affected by change in light condition, as they rely on sound wave rather than light. Second one is ultrasonic sensor are inexpensive due to their simple technology and wider use, helping reduce production costs, which is less expensive than LiDAR sensor. The last one is ultrasonic sensor detect object without physical contact, helping prevent contamination or damage to the sensor and useful for corrosive or hot materials. Challenge of ultrasonic sensor. The first one is ultrasonic sensor use sound wave to detect object and are particularly susceptible to noise. Acoustic noise at the same frequency as the sensor signal can interfere with its reading, leading to inaccurate or false result. The second one is ultrasonic sensor can be affected by environmental factors. Change in temperature and humidity can affect the speed of sound, which may cause the sensor to measure distance less accurately. The last one is ultrasonic sensor have difficulty in detecting with soft or angled surface. Soft materials absorb sound wave while angled surface reflect them, causing weak or no echo.
Future developments and innovations. Looking ahead, ultrasonic sensor technology is expected to experience significant advancement. One exciting area is the miniaturization of sensors using MEMS technology, micro-electromechanical system, which allows sensors to become smaller, more energy efficient, and easier to integrate into compact devices. Additionally, there's a growing trend of sensor fusion, where ultrasonic sensors are combined with other technologies like LiDAR, radar, and cameras. This enhances the accuracy and reliability of a system, especially in autonomous vehicle and robotics. We are also seeing the integration of artificial intelligence to better analyze sensor data, enabling smarter decision making in real time. In the medical field, 3D and even 4D ultrasound imaging have been developed, offering clearer, more dynamic views of internal structures, benefiting diagnostic and patient care. Overall, the future holds great promise with continued innovation, expanding the capabilities and application of ultrasonic sensors in numerous fields. Conclusion. To conclude, we have explored how ultrasound waves play a crucial role in ultrasonic sensors, forming a backbone of many modern scientific instruments and systems. These sensors offer numerous advantages. They are non-invasive, accurate, and perform well in various conditions. Their real-world applications, from obstacle detection to medical diagnostics, demonstrate their versatility and importance. While there are some limitations, ongoing technological advancements are steadily overcoming these challenges. I hope this presentation has given you a clear understanding of how ultrasonic sensors work and why they are such a vital part of today's technology landscape. Thank you very much for your attention.